So this is going to be a discussion on baths. Okay, so basically this is based on some work that is done with Archak Purkayastha and Manas Kulkarni, and these are published in these two papers. And so actually, I mean, this talk really should have been given by Archak, I mean, who really knows the stuff really well. But anyway, I'll try to do a explain what it's about. So the basic question we are asking, okay, so I'll just explain what is the basic question we are asking. So we look at a simple open quantum system model, which consists of, let's say, there are two sites. So, which consists, maybe it could be like a quantum dot or some coupled qubits or something. And these are coupled to two reservoirs. Okay? And the reservoirs are like, it's a 1D lattice, which again consists of non-interacting fermions or non-interacting bosons or whatever. So this is my system. And this is bath 1. And this is bath 2. And this bath is supposed to be described by equilibrium properties, let's say chemical potential, which I'll call mu1 and T1. And this path is at some different chemical potential and temperature T2. Okay, so this is the setup. And then I have some coupling here, okay, between the system and reservoirs. And this coupling strength is, I'll call it epsilon times. So I'll define the precise model, but basically there's some small parameter epsilon, which tells me how small the coupling is. Okay, so now, so I write some Hamiltonian for this bath, and this I call HB1. And for this guy, I write some Hamiltonian HB2. And for the system, there's some Hamiltonian HS. And then there's some system bath coupling, HSP1. And here there's some coupling, HSP2. Right, and this is going to be a completely non-interacting system. So basically, I'm going to write Hamiltonians in terms of like quadratic Hamiltonians for all the parts. Okay, so okay, so now the system consists of basically okay, so this setup is very generic, right? It could be like I have like a quantum dot coupled to one-dimensional metallic leads, or I could have something like maybe a small molecule which is described by a harmonic Hamiltonian and which is coupled to phonon reservoirs, or it could be qubits and so on. Okay, so this is a very generic, yeah. So the only thing we are saying is that it's a completely non-interacting system. So now what we do is, so at t less than 0, there's no coupling. And system is in an arbitrary state. And then at so at time t equal to 0, so initially these are two systems in equilibrium, and I also assume that these are infinite systems, okay. And then at t equal to 0, I just connect the system, and I connect switch on these interactions, the coupling, and then I just evolved the entire system with the full Hamiltonian. Right. So, okay, so then the statement is that uh, if paths are infinite, state. So this is usually called a non-equilibrium steady state. And okay, so I mean, this part of this also, I mean, the system will reach a steady state at long times. I mean, what happens in the bath is, of course, a separate matter. I mean, maybe like I could think of this much as the bath, then that also will reach a steady state, but not everywhere in the bath will be in a steady state. But I'm just interested in the system, and that reaches a steady state. And some interesting questions are, right, okay. And properties of steady state, we could ask like, for example, this could be, we could ask what is the current going through the system. So I'll just call it J. And so this is, this average is the steady state average. What is the current flowing from this? So there are these two sides, 1 and 2. Right? So I can ask what is on an average, how much current is going through this? Or I can ask what is the density out here and the density out here. So I could ask what is average occupation on this each site Ni, and I could ask for correlation functions. I could also ask for like things like two-time correlations, NIT, NJ0, and so on. Okay, in the steady state, I can, yeah. No, so what I'm saying is that you just prepare this bath in equilibrium, which means it's described by ensemble like some ensemble like this. Let's say one. Uh, with some normalization. So you just prepare it in an equilibrium ensemble. So of course, it's, I mean, it's a finite temperature, finite chemical potential system. I mean, you can of course prepare it in the ground state. That also you can ask. But I'm saying it's a finite temperature and chemical potential. Yeah. Yeah. No, no, I didn't say what the Hamiltonian is. That depends on. Yeah. I mean, maybe the interactions here are a bit different. I mean, I didn't specify what the interactions. I mean, like leads, usually I'll take it to be an ordered thing. And here I might put disorder or whatever, or some arbitrary. Okay, so these are the kind of questions that one is interested in, right? I mean, I can ask for equal time, I mean, properties or unequal time correlations. Okay, so now, okay, so this is, so with this starting microscopic model, Okay, so this is always for all, I mean, microscopic models of baths, this is always the starting point. The reservoirs are a bunch of non-interacting fermions or bosons, and then your system can have interactions or maybe non-interacting, but the bath model is always the same. And then you can now try to, you want to answer these questions and you can try to do it in various ways. Okay, so you're just interested in the system properties. Okay. So there are various of ways of doing it. And these are, I'll just list the various ways. And in this program, we have heard many of these approaches. Quantum. Okay, so yeah, so it's the same problem, you can do it in various ways. Okay, so if you're looking at non-interacting systems, uh, okay, and so basically for all these properties that you want to compute, you can actually find formal exact solutions given in terms of so-called non-equilibrium Green's functions. Okay, and this you can achieve by using methods 1, 3, and 4. Okay, so you can use all these three methods and they will give you exactly the same answer. Okay, answers in terms of Green's functions. So I'll talk a little bit about this particular approach which we have been developing for quite some time. Uh, okay, and so these are completely exact. And then you have this master equation approaches. Okay, so master equation approaches, I mean, like to formulate them, you need to make approximations. And so then the basic question that we asked is that okay, so basically what we'll do is we'll take this exact, I mean, like for this simple system, these two sites connected to reservoirs, we will use this approach to get exact answers, and then we'll compare with what is predicted by Redfield and Lindblad. So Okay, so this is that's the basic question. Within the system also non-interactive, right? Yeah, yeah. That's the only case where you have exact solutions. Okay, so right. Okay, so now let me just write the precise Hamiltonian that we work with. So the Hamiltonian is, is the concept of the system. So the system is there's some. Okay, so there's some on-site energy and there's some coupling between the sites. And then I have the two baths. So the baths are, so there's some, so it's just a one-dimensional chain of particles. And so I write it as Hermitian conjugate. So this index is for bath 1. And then I have similar thing for, so maybe okay, so it's just a tight binding chain, right? I mean, that's the bath, and this is the bandwidth of the bath. And then the interaction is the usual. Yeah, exact analytical solution, right? Yeah. Exact analytical. Okay, so I mean, for example, if you want to find the uh, okay, so everything is given in terms. Okay, so there's some, let's say, for this tight binding Hamiltonian. So there's a okay, so this. So I should just say that like some Hamiltonian like this, I can always write it as right. Some basically it's some n cross n matrix if there are n sites. Okay, so I have the Hamiltonian, and then I have all this coupling matrix. So basically, I can define a Green's function like uh, some sigma. Okay, so I can define some Green's function for the system involving the leads, and then everything like can be written in terms of this G and this sigmas. Like the current is, for example, the current is given by this kind of Landauer formula, right? So a formal means in the sense that you can't always do the integral, but it's an exact formula. I mean, in many cases, you can actually do completely evaluate it. No, I mean, okay. So in the no, in the non-interacting case, you can write it. Okay, so this is much better than that. It's more explicit. Like if you want to do, you can just put it on a computer and completely calculate it. I mean, it's just some up to some integrals, doing some integrals. That's what I'm saying. But it's known completely. For non-interacting systems, you can't. You have to make further approximations to, like you might have some Green's, the self-energy terms which you, to evaluate, you have to make approximations. But here it's known completely. So in that sense, it's exact. Yeah, for But even for Kondo, non-equilibrium Kondo, I don't think it's completely exact. Like, huh? No, but it's since you don't know the self-energy. You're saying it's Nathan Andre's thing, but it's not completely exact. I think, in fact, no, it's not completely exact. Yeah, the scattering thing, but yeah. Yeah. No, so the leads, the connection. No, this can be just at one point. That, right, yeah, that's enough to equilibrate the system. I mean, to make the system reach a steady state. Right, yeah. Okay, you're asking if I have some, let's say, some arbitrary network, and I connect it to just 2 points. Right. Okay. So first of all, I mean, there are some conditions under which you'll get a steady state. Like the reservoir, like the bandwidth of the reservoir should be large enough so that it contains the entire spectrum of this guy. If that is satisfied, I think it will reach a steady state. The bandwidth should be bigger than that, right? Yeah. I think that's right. Yeah. Okay. So yeah. So this is the. Okay, so just to make it clear, these are what I called as B11 and so on. So I label B's this way, B2, 1 and so on. And these ones are B1, 2, B2, 2 and so on. Okay. So that's why this guy just couples to this guy and this guy just couples to this guy. System is there, right? The Hamiltonian. It has like two sides. There's some on-site energy and you can hop between the sides. That's the, sorry? No, that's the definition. I mean, that's it. I mean, there's nothing else. I mean, if you want, you can couple it to phonons or that, but that would be a different system. Right now, there's nothing. That's it. Okay, so given this system, what you can do is uh, you can just for the system variables, what you can show is that it's possible to write Heisenberg equations of motion. So so in this case, it's just A1 and A2. So these are the system variables, A1 and A2. And what you can show is that they are in general given by so I'm briefly explaining the Langevin equation approach, which is actually one of the simplest ways. I think it's really the simplest ways to get this steady state. I mean, the steady state results or correlation functions in this kind of systems. Okay, so Okay, so I won't go through the details, but if you write equations of motion for like the system variables and the path variables, and then you just solve the path variables because these are all linear equations, and then plug it into the system variables, this you will get an equation for just the system variables, which looks like this. So now in this term, this term eta 1t. So remember this term basically came from the interaction of the system with the bath, right? And so when you solve the bath equation, you get this term plus this term, which depends actually on the initial conditions of the bath. Okay, so this guy actually depends on the properties of the bath variables. So EL1 at time. Okay, so here let's say I switched on the bath at some time t naught. So it depends on the path properties at time t naught. Okay. So at t naught, I assume that it was in equilibrium. So I know, like, if I want to compute any correlation function for this noise, I just use the correlation functions of the bath, right? So I know all correlators of this noise because it just depends on the bath initial conditions. Okay, and then what I also find is that this correlation functions actually depend on this, and that's like a fluctuation. It's like exactly a fluctuation dissipation relation. So this is like a usual classical Langevin noise where the noise satisfies the fluctuation dissipation relation. And now these are again linear equations, and you can just solve them by Fourier transforms. Okay, so so you assume if you are just interested in steady state properties, then what you can do is you can set this time t naught when you switched on the bath to minus infinity. Okay, and then it's in the form where you can do a Fourier transform. So if you do a Fourier transform, then it's a linear equation. So it will basically look like A L. So this maybe okay, so. Yeah, yeah. Equilibrate at? No, because there are two baths, right? I mean, if it was, if both the baths were yeah, yeah. So right now I'm interested in, supposing I'm interested in steady state. So if so using this approach, getting time transient behavior is difficult. I won't talk. I'm just talking about steady state properties. Then you need really T not to be starting from zero. But I'm just interested in transient properties. So I just plug it in out here, and this sigma I also define as. So these are the definitions of the Fourier transforms, and similarly for noise. And then it's easy to see that what I get is A L QED omega is equal to my. Okay, so now it's a simple linear equation, and so if I think of A as a vector of like A1, A2, in general, if I have n sites A, n, twiddle, and this I call A, then the solution of this equation is given by A tilde omega is equal to some G omega. So where G omega is equal to 1 by okay, so right, okay. H of, I mean, I wrote there what is H. No, I wrote, I mean, I defined this system Hamiltonian as H. No, this is a different H. This is a, sorry, early H. That's just, it's just n cross n matrix. It's not the second quantized Hamiltonian. So this is just n cross n matrices, right? I mean, and these are also n cross n matrices where the first element is 1 and this is sigma 1 omega and this is another. Okay, so now this is the Green's function and this sigma omega is basically given in terms of some properties of the bath. Okay, and so I think I won't explain how it comes, but basically this sigma omega is given by gamma square delta omega minus I j omega by 2, where j omega is a function which is uh, okay, and delta omega is okay. Delta omega is related to j omega by some transformation. Okay, so now what are these k, kappa, 1 alpha and omega alpha? Okay, so when I wrote the system bath interaction, so this was my system bath interaction. Now I can for the bath I can go to the the eigen basis of the baths, right? So this was the bath, but I can equally write it as because it's a quadratic Hamiltonian, so I can just diagonalize it and just write it like this, where let's say Bs so I'm just writing it, I mean, ignoring the indices 1. So if I make some transformation, Bs is equal to Ks alpha B alpha, then I can bring this thing to a diagonal form. Okay. So this is just the, I mean, normal mode transformation. So I have to find the eigenstates of this Hamiltonian and then I can do this transformation and make it at this variable. Okay, so this K, so out here I have this, okay, so now if I use this transformation in the coupling, then I can see that my site is actually coupled to all the modes. Even though in site basis, it's coupled to just the first site, in the eigenbasis, it's actually coupled to all the modes, right? And the coupling strength is given by K1 alpha, because it's the first site. So so that's where this K1 alpha comes. Okay, so it's a property of the bath. I mean, it's without any, so it's a complete property of the bath. The spectrum of the bath and how the first site is coupled to all the modes of the bath. Okay, so that defines this spectral function j omega, and this is the central quantity that is everything is going to depend on. So okay, so I can write this thing in terms of this, and then since I have a solution, now I can, if I want to compute any properties like AT or I can just use the solution, and then I also know the noise-noise correlations, which are again can be expressed entirely in terms of this j omega and the whatever. So the other quantity that comes is the it's either the phonon or the electron distribution function. So so this n omega. So basically the noise-noise correlations can be expressed in terms of n omega and this j omega. and they satisfy a fluctuation dissipation theorem. Okay, so so this is the quantum Langevin approach. Now, what I want to say is let's go to the Redfield equations. Okay, so I wanted to kind of give a derivation of the Redfield, but there's just 4 that includes question time now. It includes 5 plus 4. Okay, okay. So I don't think I can go through the derivation of the Redfield equation, but yeah. Oh, you can't do the Fourier transform solution. That's the, I mean, here you could solve everything because you just take Fourier transforms, and if it's like you have the only thing that would be, here you'd get some square or cube terms, right? Like in the A's. I mean, these terms would still be the same. Right, yeah, it won't have the linear structure. That's the big problem, yeah. Okay, so so here the basic idea was to use, for nonlinear, I mean, you have to make approximations. Yeah. Then you have to do approximations, and usually it's uncontrolled. Okay, so now master equation. Okay, basically you, instead of working with Heisenberg equations of motion for the observables, or for the basic operators, you look at try to write an equation for the density matrix. So you start with this general equation of motion for the density matrix. And then, okay, so again, I won't go through the steps. So this is for the full thing. And then you define the system, which is given by trace of, and it's exactly the same setup. Like initially, it's the uncoupled bath and system, and then you want to just look at the system properties. Okay, so you want to trace out the initial condition of the baths and define this reduced density matrix of just the system. And then the equation that you get typically looks like this. So this is now reduced density matrix of just the system. So there's a system part, and then there are 2 parts coming from the 2 reservoirs. Okay, so L1 rho S plus L2 rho S. And okay, so I mean, so you can start from this full thing and try to do try to derive this, and you have to make 2. So first point you get is what is called the Redfield equations. Okay, and this involves 2 approximations. One is basically you say that at all times rho of T is basically like rho of S T product rho of R. So you assume that at all times, somehow you still have this product structure where the system is, the bath is kind of still in equilibrium. So this is called the Born approximation. And then you have to make another approximation which basically, when you solve this somewhere, so you have to assume basically like correlation functions are kind of decaying very fast, okay? And some point like you get an integral equation and you have to replace rho t prime, so there's a memory effect, and then you say that instead of like integrating over all the past, you replace this by just rho t. Okay, so using these 2 approximations, you get this set of equations. I won't write the structure, but basically this guys will still involve this same set of functions, j of omega and n of omega. So all information about the baths is contained basically in this j omega and n omega. Okay, so you can write these equations, and then you can, for this 2 particle system, you can just solve them. Okay, so the other thing that we did is, okay, so these equations in general, it's, I mean, if you have n sites, it's the Hilbert space is like, for bosons, it's infinite dimensional Hilbert space, right? So it's still hard to solve numerically. So what you can do, again, for non-interacting systems, which we did, is that you can write an exact set of equations for correlation functions. So if you define any, So if there's some correlation matrix, then you can actually write an exact equation for this correlation matrix, which is basically some linear equation plus some inhomogeneous part. Okay. So this is a n square cross n square matrix if you have n sites in the system, and which is easy to solve numerically. Okay, so this is Redfield, and then to get Lindblad, you need to make one more approximation, so-called rotating wave approximation, and that has a even simpler structure than the Redfield equation, and still involves the same set of functions. So now I'll just quickly state the final results that we got up when we compared these three methods, exact, Lindblad, and Redfield, and I'll just summarize very quickly. Okay, so we computed the current in occupation, and we also looked at a steady state, and so one is in the steady state, and two transients. So for transients, you can't use the analytic methods. Here we just did exact numerics. And the final result is that Redfield is good for small epsilon. And okay, so if the system path coupling is weak, then it seems to be always, most results, it reproduces quite, both transients and steady state, it reproduces quite well. On the other hand, Lindblad, okay, so there are various versions of Lindblad, and the two sort of popular versions are called local and eigenbasis Lindblad. Now this one, it works only, it's good only when the coupling within the system is very small. So the coupling within the system was this G. So if G is small, and of course also epsilon, I mean, so this is, so I'm not saying exactly what small means, but compared to some quantity. So if both are small, then it's good, otherwise it's quite bad. Okay. And the local, if G is small, local becomes the eigenbasis. Okay, but then you'd ask, is the eigenbasis always good? But the eigenbasis is good for, okay, it's good even when G is not small, but for properties like occupations, but not for like things like current and all, it doesn't reproduce. Okay, so if you want current inside a system, is current inside system is 0. Cannot be obtained, okay. So some properties it just can't get, but some properties it does capture, okay. G was the coupling within the two dots. So I mean the local Lindblad works. I mean, so in the local Lindblad, basically when you are coupling the Lindblad only to the end site, right, not to the eigenmodes. So in that case, you have to put so in the local Lindblad, basically you have to add some terms like maybe A1 dagger rho A1, and the coefficient has something like so you need the distribution of the phonons, right? Now you have to put a frequency here, and you typically put the frequency of the site. You can't put the information about the eigenmodes into this. Okay, so it basically therefore it equilibrates locally. And if there's a strong coupling, then the system is, I mean, you do not reproduce the okay, so small against, right, yeah, so that's what I didn't specify. I think it's small compared to the coupling with the reservoirs. Arshak, is that right? Small with respect. Yeah. Right, yeah. So, I mean, if it is small compared to epsilon, it works. I mean, like that's empirically observed. I think we don't have a clear statement of when it will, but empirical observation is that when it's small compared to the coupling, it works to the reservoirs. Right. Yeah. Okay, sorry. Yeah, sorry. I should. Yeah. Okay. So. Okay. So that's the summary. So the main message is okay. So one is like we have this. Very nice set of equations from which for any like arbitrary non-interacting systems, I mean, it need not be two sides, it can be in any dimension and so on. You can actually solve for steady state properties using Redfield equation, which is usually quite difficult technically. And then we have these results about like comparison between these various methods. And some interesting questions are what happens when you have large system sizes and all. I mean, it's not clear that this master equation approaches will always give the correct results, even qualitatively. Okay. So yeah, so I think I'll just stop.
Does someone feel a particularly urgent question? I guess Prasanna didn't ask one yet. But a comment? Okay.
Yeah. It's yeah. Yeah, in many cases it just doesn't equilibrate, so it's a bad bath. Like local Lindblad, for example, if you have large chain, you couple it at the ends, it's really a bad bath. It should at least reproduce equilibrium. Yeah.